that's super problem specific, but a few overall trends that I was realizing that I'd like more clarity on as I was working
Oh,
through it.
okay.
Um, so let's see. For starters, when I was going through problem 5D of the 9.3,
5-3, or sorry, 5.
9.3 problem 5D.
Okay, 5D. Okay.
Gotta find it too. Okay. So it's that like rectangular thing.
Okay.
I was wondering, what kind of methodology do you use to make sure you find all of the symmetries that make up G? Because I found myself wanting to add in two, maybe even four more elements of G than are actually supposed to be there when I compared it with the answer.
Okay. So let me see here. I'm going to draw a picture.
Sure. And I did work through the problem and understand it, except for when it comes to choosing the symmetries.
Okay. So 5D is, it looks like, I mean, it looks like it's somewhat intentionally shorter in that middle edge.
Yep.
Is this it?
Yes, that's the one.
Okay. So then ABC, and it wants us to color the vertices of this thing.
Yep.
This is 9.3 5D. So what symmetries were you thinking about?
Okay. So the ones that they end up doing are 0-degree rotation about the very center of
Yeah, 0 degree.
rectangle
Yeah,
BCFG. And then
right.
they also say 180-degree rotation.
Right. And that makes sense, doesn't it?
Yep.
So that central point that I marked with a red dot is what we're rotating about. It
And
doesn't
then they
matter.
also do reflection about the vertical line and the horizontal line through that red dot.
Yeah, yeah, that's right.
And those are the four symmetries that they say.
Okay, so and essentially this, right, the 180 degree or actually 180 degree rotation, right? So all the way over to there, heavy one.
Right.
But of course, 90-degree rotation doesn't work here because it's like rectangular and it's not square, right?
Hmm.
Okay, so we also have this and this.
Right.
What others were you wanting to do?
I had remembered from discussing the cube example back in lecture that we had talked about identifying symmetries um, by revolving the cube around line or an axis drawn from every pair of vertices, every pair of edges, and every pair of faces. And I was wondering if that's like a general trend or if that's something specific to the cube. Obviously, here we have a 2D image, and so that would affect it somewhat. But for that reason, I was kind of thinking, okay, should we try to draw an axis of reflection between vertices? And so what I thought about doing was like, say, trying to reflect the object from over the axis from H to D and from A to E.
H to D?
Yeah, if you could kind of rotate it around those two corners.
Yeah, but the issue is if you do that, if you reflect in that axis, Logan, DE is pretty clearly a lot shorter than AD. Yeah,
Okay.
DE is a
Right.
lot shorter than AD. So if you reflect across that thing, AD is going to be going downward. Does that make sense?
Oh, okay. So it switches from being like this to being like this.
Yeah, basically, just the essence of what's going to happen. Well, in fact, it might even be some kind of weird, since this angle right here is like shorter, is smaller than this angle, it appears. It might end up being some other kind of weird thing, like
Since
I guess you would still have, like, of course you're going to still have a 90-degree angle, but it's going to have a long side below the axis of reflection, namely AD, and then a short side DE on the other side, which isn't going to be right.
what? I'm still confused. What are you talking about as far as the angles go? You said one was bigger than another.
So if I reflect this across here, I mean, let's see if I can, let's see if I can try to draw the reflected image down here. So D is going to stay where it was, right? H is going to stay where it was. I think it's going to be something like this. Where this is DE, and this is H, and this is A. Okay.
Okay.
So, I mean, that's what I meant by this big angle right here. The angle that goes from the axis over to the line DE. Like this angle is bigger than this angle. It looks like that's the case. So then what happens with the other two things? So if I flip those up there, it's going to be G and F right here. And then B and C right here. Does that look the same when we do that reflection?
Nope.
Yeah.
Okay.
The issue is the core issue is that one of the sides is longer than the other. So,
Okay.
I mean, does that picture make sense, what we just did?
Yeah, that makes a lot of sense. One thing I've realized I've been kind of having to train my mind to be able to do is better flip images in my mind.
Yeah.
And it seemed to be, as you've been doing this, one of the tricks you commonly do is if we're looking at that vertex or point D, you just kind of flip the things that stem from that and then let that play out to the rest of the figure.
Yeah, right. So just kind of think about possible destinations for a vertex.
Right.
And it seems like once you determine a possible destination for a vertex and an edge emanating from it, you're done. But you still have to think about whether every destination is a legitimate one. And in this case, it wasn't. I guess essentially what we were trying to do here, I mean, the thinking was that like maybe G and A and E and C were somehow interchangeable with one another, but they're not. They play like fundamentally different roles in the figure. Whereas, I mean, like in the icosahedron, for instance, every vertex is basically like every other vertex. Does that make sense? So the way in which we construct these symmetries is based on, vertices going to other vertices that where it's playing the fundamentally same role. So like for D, that would mean either going to E or to H or to A. Does that make sense? So like let's just talk about A. What are some places that A could go? Well, it could either go to itself, right? Or it could go to D, and that's what happens if I do the vertical axis flip, right?
Mm-hmm.
Or where else could A go?
You go to H.
To H. That's what I get when I do the horizontal axis flip. Or where could A go?
Could I go to E?
Yeah, E. And that's exactly, that comes from just doing a 180-degree rotation. So
Okay.
the fact that we've kind of cared for every possible destination for vertex A is starting to convince me that we have them all. Does that make sense?
Okay. So you
Yeah.
said you would compare A with every one of its possible destinations, and for it to be
Yeah.
considered a possible destination, it has to be serving a similar function.
Yeah, that's exactly
Right
right.
figure?
Yeah. Because B
Okay.
and C and G and F and G are like in the middle of a side. Like A doesn't play that kind of a role at all. So
That makes sense. And so that's one way that you would use to help make sure you got the right number.
yeah, or to help me kind of think about possible symmetries. I mean, that seems to be working. When we went through all of the Platonic solids, that seemed to kind of be the key, right? We focused on an edge also. But here, I mean, I think that if you if you think about edge AH, there's really only one place where the edge AH could go, or two places. Either it can stay where it is, except maybe just flop the rolls of A and H,
Mm-hmm.
or it could flip over to DE and flip up or down. And again, that's four possibilities, and those all come from those four symmetries. So just thinking about a vertex going to some place that it plays like the exact same function, and then like an edge emanating from that vertex where it could go. I mean, that usually will give all of the symmetries. And you could do similar things with edges and faces.
Gotcha. When we were working through the Platonic solids, another kind of guardrail that you were using as we were going through that was the fact that the maximum number, or we calculated the maximum number of possible symmetries
Yeah.
based on seeing all of the places you could put a vertex and an edge. Is that something we could do with a 2D diagram, or is it something
Sure.
that would not be fruitful?
Yeah, sure. Remember when we tried to figure out the number of symmetries for, like, let me just draw a picture here. So how many symmetries of the regular pentagon are there? Well, there are, how many places could A go? Okay, so let's concentrate on A and maybe this edge right here.
Now, real quick, why do you pick a vertex and an edge when you're doing this?
Well, because I have to think about this edge potentially flipping over to the other side. Because I could rotate, I could rotate A around, yes, but then
Right?
this edge would always be oriented to the clockwise right side of A. But that edge could also go somewhere else. It could go to the counterclockwise left side of A. Yeah. I mean, I could flip that edge over there if I really wanted to and get a new symmetry. Okay, so how many possible destinations are there for A?
There are 5.
Yeah, so there are 5 destinations for A. And how many for the edge? Once A finds a destination, what's that?
2.
2. 2 for its edge. And by its edge, I mean the one that I've distinguished. So for instance, that thing could go, A could go down here. And if its edge stayed on the same counter or the same clockwise direction, it would be this, right? So A could land right here on this vertex. And if I don't flip the edge around at all, it would just go to right here. But another possibility would be for A to go here and to also flip that edge around so that it goes here. Does that make sense?
Yeah.
Imagine that thing kind of rotating, right? Rotating around. So what's the maximum possible number of symmetries here?
10.
Max symmetries equals 10. And in fact, there are 10. There's there's 0 degrees. There's, oh man, sorry, I have to think about this. 72. What's 360 divided by 5? Is that 72 or something? Yeah. 72 degrees, 144 degrees.
Yeah.
216 degrees. What's the next one? 288 degrees. And then you're back to the beginning. But then you also have all these weird symmetries, or all these weird reflections, where you go through a vertex and an edge. How many vertex edge pairs are there?
5.
5. You have this one, you have this one, you have this one. Or wait, yeah. Oops, I missed one. Okay, you have the vertical one. You have, this one that's like slightly like this. Okay. What other one do you have? This one. Okay. This one. Okay, and this one. These two aren't very distinguishable from one another, but so I mean, I'm writing all of these different reflective symmetries. Okay, and I found 10. The ones that do the job of flipping the edge around are the reflections. The one that does the job of moving the vertex around are the rotations. Yeah. So
Okay.
So I have complete confidence that there couldn't possibly be any other symmetry, because I've accounted for all possible destinations of a vertex and an edge. Yeah.
Gotcha. So kind of extrapolating this method out a bit, say we were looking at a new figure that we had never seen before. And it was kind of different than, say, an n-gon or something like that.
Uh-huh.
If you calculate the max number of possible symmetries like we did, obviously, or for me at least, the simple rotations are pretty easy to think about. But like, what would have made you think to try symmetries of reflection about a vertex and an edge? Because to me, that doesn't seem super intuitive right off the bat.
Well, I mean, it has to look exactly the same on both sides of the line of reflection. It has to look exactly the same. So like up here in this example that we were doing, it doesn't look the same on both sides. It looks like it it looks like an inverted image of itself. Does that make sense? Like there's, if I'm kind of starting right here at vertex D, I see long side, short side. Whereas if I go in the direction, it's like short side, long side. But whereas over here, I'm saying, okay, are there lines of reflection where it literally looks exactly the same, on both sides? And the answer is yes. But I can't go through like 2 vertices. If I go through 2 vertices, it destroys the symmetry. So I just kind of say, oh, there's a vertex and an edge, and it looks exactly the same on both sides. It's a mirror image of itself. Whereas this other figure, it was not a mirror image of itself on both sides of that yellow line of reflection, potential line of reflection.
Okay.
So I don't know. I mean, the best advice I can give is, you know, just kind of think about, okay, where does this thing have mirror image symmetry? And in the case of the pentagon, the answer is through a vertex and the middle of an opposite edge. If it was if it was like a hexagon, well, I feel like you would have a lot more symmetry, wouldn't you? So here, 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 I didn't draw a very symmetrical picture, but here, here, here. So every single pair of opposite edges and opposite vertices. Oh yeah, that's not like a lot more symmetry. It's just there I was pairing off opposite vertices and opposite edges, right? So I ended up with exactly 6 lines of reflection, right? 1, 2, 3, 4, 5, 6. Whereas on the other one I had 5 lines of reflection.
Okay. And then I think that makes sense. So those are what kind of the tricks that and ways of thinking about that you would recommend for other problems.
Right. Yeah. Just look for mirror image symmetry. Think about destinations of vertices. And again, a vertex can only go somewhere where it plays the exact same role. Think about an edge coming off that vertex, where it could possibly go and still preserve the symmetries. So yeah.
There were 2 other symmetries, possible ideas I had for symmetries for that rectangle up there as well. And those were extra rotations. I was playing around with the idea of making the axis of rotation be the exact center of rectangle A, B, G, H, or C, D, E, F. So why wouldn't those work?
Well, because it doesn't look the same. I mean, if I were to rotate around this, right?
I was thinking it could float in space, right? So what's to keep it from rotating like this and then sliding it over so that it's...
Well, that's a rotation followed by a translation. And that's exactly the same. So if you do that, that's exactly the same as, right? If I were to rotate around that point and then slide it over, so that's a translation, a rotation followed by a translation. But that's, I'm telling you, that's equivalent to something else you already have.
Right, it is.
Basically doing both reflections or something. Does that make sense? Yeah.
Yeah.
So that only accomplishes something you already have.
Okay.
Oh, yeah.
So typically we don't allow for translations, right? Because I haven't seen you use those ever in any of the examples.
Well, no, because the translation, I mean, typically you do allow for that when you're doing symmetries. But if you want the thing to stay in the same place to where it literally looks the same, a translation would destroy that, right? I mean, a translation would move it from one place to another place. The thing is, I want to be able for you to like go out of the room, for me to do the symmetry, and then you come back and be like, well, what did you do? The only way you would be able to tell the difference is if I were to label the vertices or color them or something, right?
Right.
I want you to be able to leave the room, me do the symmetry, and you come back in and say, what did you do? You didn't do anything, you know?
Okay.
That's the definition of a symmetry. You know, if you translate the thing, you're going to say, why did you move it over there?
Right. Okay.
Yeah.
So the issue here is not mainly the fact that that would be employing translations as well. It's because we already have that type of symmetry.
Yeah, that's already accounted for.
Gotcha.
I mean, we would only employ a translation in an effort to put it back to where it was before.
Right.
and uh, and that's already that has to be accounted for by those 4 other things.
Gotcha. And then one last observation with symmetries that I've been noticing is that in some of the problems in the homework set, we'll be looking at M colorings for vertices, and then later on we'll end up resolving the same problem with M colorings of edges.
Mm-hmm.
And I was noticing that it appears like if you left the vertices labeled the same way for both types of problems, they have the same set of symmetries. Is that true
Right.
in general?
Yes, you will have the same sets of symmetries, but the permutation induced is going to be different, right?
Right.
So yes, the symmetries are exactly the same. They have to be, okay? But the permutation induced will potentially have a different number of elements, right? And
Mm-hmm.
and potentially a different cycle structure as well,
Right.
which is
Okay.
the key for applying Burnside's theorem in all versions of, well, actually the cycle index polynomial
Yeah.
construction.
Okay.
Right observation.
When I'm working through problems, how much of my work would you like to see during the transition from where I go from, okay, this is the elements of G when they're strictly written like you did at the top of this example here, to, okay, this is the cycle index polynomial. Do you want to see the whole cycle structure written out? Because for some of those, it's like pretty lengthy. And I did do it. But then like other times I noticed in examples you were doing, you would just kind of say, oh, notice that like this category of permutation and or things induced by this category of permutations all yield the same type of term in the polynomial.
Right, and so you just add those one. There's 15 of those, so 15 of those. Yeah, that's fine.
Right.
You can say this permutation gives rise to this cycle structure in the cycle index polynomial, and there are 3 times 5 equal to 15 of those. The end. I mean, so that's perfectly acceptable. Yeah.
Okay. Well, I'll start doing that in the future, but I gave the full messy details on some of those problems after I typed them up.
Oh man. Well, that's probably good for you though. I'm sure. Really gives you a full-throated understanding of what's happening.
Yep. Okay.
Fair. I mean,
Go ahead.
yeah, this is pretty surprising stuff. Like, right? I mean, what business do we have counting these kinds of things?
Yep.
I mean, it just I every time I think this through carefully, I just find myself being re-amazed by it and thinking, what in the world?
Yeah. I had this moment of realization the other week when I noticed that a lot of the times when I report my answers, I don't actually calculate the numerical value, and I leave it in some like combination form or something like that. So I don't actually know the magnitude of what we're counting. But one time I converted the answer to its numerical form, and it was for that chessboard problem.
Oh man, where it was like 2 to the 64th plus 2 to the 17th. Yeah, that thing's it's going to be like close to 10 quintillion or something like that. Yeah.
Yeah, it was. Assuming I did the problem correctly, I don't remember what homework set that was in. It was at least in the, I think it was in the quintillions, which was like, that's insane.
Yeah, it's going to be in the quintillions because 2 to the 64th is roughly, I think that's roughly 9 quintillion or something, 9.28 quintillion. The only reason I know that is from computer science. And that's sort of the dominant term
Yeah.
in that example. So that was amazing. Can you imagine? You're like, oh, so you just counted them all, but of course you have no idea, like, there's no possible way you could ever list them all, right?
No. That's insane.
But it
Okay.
just
Well, I
doesn't.
think that helps a little bit.
I mean, think about that chess problem, though. I mean, there's no way. How would you have ever done that? You know? But now you know the answer. So to me, that's
Hmm.
cool. Yeah. Hopefully you feel the same way. Trying to convince you to feel the same way. So
I think I feel a certain degree of that excitement.
okay. Yeah.
Needs to be cultivated a bit more.
Yeah. All right. Well, cool.
Hmm.
Well, I hope things are going well for you.
Yeah, I had a few other questions for you too,
Yeah.
that are kind of unrelated.
Okay.
If that's all right. When I'm just kind of like mentally preparing for the next exam, that's going to be, I don't know, in a week or so, probably. Is that right?
Well, I'm gonna send out a take-home test, and then it'll be due like next week at some point.
Okay. Um, Again, is that one going to be open book, open homework sort of thing?
Yep.
Okay. Is it going to be, is it open office hour videos? Or like, what's your policy on
Yeah,
that?
sure. That's fine. I mean, any sort of course. I think I've just been saying any course-related materials, which of course
Okay.
include the YouTube videos. I mean, the
Okay.
queue of those is getting fairly large at this point. So, I mean, you may have to. It may be hard to find stuff, but I mean, we have been keeping somewhat good track of
Yep.
certain things in that document. Um, so yeah, and there are sometimes. I think the reason Aaron made that document is he noticed that I was answering a lot of the same questions. But so I think he was trying to help me out a little bit. But in some sense, it's helpful to have it explained multiple times in multiple ways. And sometimes it wouldn't be as clear the first couple of times, But
Mhm.
we've definitely gotten more efficient with some of that. But yeah, definitely that would all be open, open to revisitation. Yeah.
Good to know.
I think you'll enjoy it.
Um,
And remember, I told you that you better know how to do the dodecahedron.
yeah.
Someone asked me about that in office hours, so.
Yep.
I think Katie actually made a floating object because I actually don't have a dodecahedron solid, which I regret. I actually found one time at like TJ Maxx, but it was just some modern piece of art or something that they, to set out on a coffee table. I was like, oh man, there's a dodecahedron. And then, but then the problem was there was like this small mistake where there was one side. It's like they didn't do it quite right. There was one side that had 6 sides on it, or there was one face that had 6 sides on it. And I was like, oh, I can't believe this.
Bummer.
Yeah. Anyways, there are lots of cutouts you can do on the internet if you want to have something in your hand.
Yeah, that would definitely be helpful for some of those. It's like, okay, I can't quite picture that. Oh, but I was working out. I'd end up holding up my block eraser to try to pretend it was a rectangle or things like that.
Yeah.
Okay. And then let's see here. I had 2 last quick questions for you about, let's see here. Well, so you said that since the symmetries are the same regardless of whether we're doing edges or vertices, then for finding the max number of symmetries, we could do that same vertex edge method, couldn't we?
Yeah, because I mean, think about it. A vertex and an edge, there's also a face that you could pick out that, touches that vertex and edge. So you can almost think of those 3 things being glued together and moving around and thinking about, okay, where does this face go or something, right? And the same game is going to get played. So yeah.
And then I was wondering, is there a general convention when it comes to ordering the terms like powers of x? I ran into this question when I was writing down my answer for one of the cycle index polynomials for one of the problems, as I didn't know whether it was better to go from like the highest power to the lowest power or the other way around. And then like even within a given term, if you have a x1 to the fourth, x2 to the third, which of those x's goes before the other one?
Yeah, I don't know that there's necessarily a convention. If I guess if there is one, it would be to write them in the order of lengths of cycles. So like any x1s always go first, even if there's a massive power on that. X2s always go second, etc. I mean, but that, that's not totally necessary. It's just kind of, it makes sense to write x1 first and x2 if it's there, and then x3.
Yeah. Okay. That's kind of, I think, what I ended up doing. Okay. Awesome.
Hey, you did a good job on your your presentation. I went and checked that out.
Oh, really?
Yeah.
Well, thank you.
Yeah. So did you have a good time with that?
I did. It was a little stressful, but would have been a lot more stressful if it had been in real life and not over Zoom.
Yeah. Right.
But it was fun.
Yeah, those pretty good presentations. Yeah.
I was surprised to see Dr. Mack there. He's in my Sunday school class at Dayton Ave.
Oh wow. Yeah.
But I didn't even think to invite him because I didn't think he would come. And then he came when I didn't invite him. So I was like, how did he even get the link for this? So it was interesting.
Yeah. Well, I think
But he said he
he's on
somehow gets
all of
like
the
all of the emails.
he's on all of the departmental like I think he gets all of those departmental emails, so he probably saw it and said, I'm gonna pop in there.
I don't know how he would keep track of all those emails. That's crazy. And then my last question for you, and this is purely out of curiosity, but if you look in the back of the textbook, they have an answer for problem 9.47D.
7B?
D.
I don't have a 9.47B.
Really? Let me double check. I thought I did.
I just have number 7. Oh, I'm sorry. Yeah, it says a repeat.
Oh, sorry.
5. Yeah. All right. So this is the figure we were just working with. Okay. Edge 2 colorings.
So it's like the pattern. What do they call that?
Pattern inventory.
Yes, for that problem.
I don't.
And it's like.
So I don't think like edge AH has to. I mean, for instance, edge AH is not the same length as edge AB, right? So AH, the only possible place that edge AH could go would be ED, right?
Right. But like I did work through this problem, but I was just curious. If you look at the answer, it's like 1/4 times that quantity. So I ended up plugging that into Wolfram Alpha, just because I was curious to see what it was, and Wolfram Alpha couldn't calculate it. I was surprised. Is it that massive of like an expression?
Yeah, that's not too bad. I mean, I did something worse than that.
Okay, so I don't know what was going on, but I plugged it in, and Wolfram Alpha was just like, it showed that it was like working on it, and I did it for like, I gave it a good 2 minutes before I closed the window.
Well,
So
here,
for some reason,
yeah, I can do this real quick.
okay, I was just wondering if, yeah, if there was something on my end that had done that, or if it was just, I don't know. It was
I
a little
mean, I
weird, I
can't
thought.
imagine that's that horrible. So let's see. And that one, I mean, I'll do some stuff in tomorrow's lecture where there are some cases where you can fairly easily calculate the thing by hand, which is a convenient thing to be able to do. But this is b plus, so it's b plus w to the 10th plus b squared plus w squared. What does it say, to the 5th plus, what's next? B plus W squared times,
Do you want me to read them off to you?
sure,
All right, let me find the, wait a second, 9.4, right? I lost my
yeah,
section. Okay, let's see, which term are you on? B squared or W squared to the 4th? Oh, so it's just, there's just one left.
yeah,
B plus W to the 4th.
yeah. Oh, oops, I put B plus 2. That's not good. Yeah, B plus W to the 4th, and then B squared plus W squared to the
3rd.
3rd.
Yep. And then you're dividing that by 4. Okay.
Yeah, there it is.
That's super weird. I must have had some sort of error in my entry, but I thought I double checked it.
Is that the right thing? So B plus W to the 10th. Yeah, it looks pretty good.
Okay. That's good to know. I didn't break Wolfram Alpha then.
Yeah. So, wow, cool.
Awesome.
These are for edge colorings, right?
Yes.
Okay.
Well, thank you for your help this morning. It's been really, really helpful.
All right. Cool. Well, I'll let you get back to whatever you're doing.
Okay. Sounds good.
All right.
See you later, Dr. Hammett.
See ya.